And now we are going to be looking at subsets. There are many situations in which there are smaller sets within larger sets. For example, if E is the set of letters in the English alphabet, then the set E contains the set of vowels and the set of consonants. We note that all members of the set of vowels, let's say V, are members of the set E, and therefore V is a part of E, or V is said to be a subset of E. Let's look at another example. Let's say A is the set of numbers from 1 to 20. Then the set A contains some odd numbers, some even numbers, some multiples of 5, and even some other groups with a common property. All of these considered separately as sets themselves, and they all form part of the set A. Since each is part of A, then each can be called a subset of A. So let's look at the notation for subsets. If all the members of a set A are also members of a set B, then A can be said to be a subset of B. This is written as follows. And so the phrase is a subset of can be symbolized by this symbol. Also, the phrase is not a subset of can be symbolized by this symbol. So let's look at some examples of subsets. Say the set Q, which is a set of all letters in the English alphabet, may have the subset P, which is the letters A, B, C, and D. It may also have the subset V, which is all vowels in the alphabet, or the subset C, which is all consonants in the alphabet. So when we have a set, how can we tell how many subsets there are for this set? Well, when listing the subsets of a set, we must note the following. The empty set is a subset of every set, and the set is a subset of itself. If the number of elements in a subset is less than the number of elements in a set, then we say that the subset is a proper subset of the set. So using the principles we have stated, we can derive a rule to calculate the number of subsets within any set. So let's look at a few sets with different numbers of elements and derive their subsets. Firstly, let's look at the set X with one element, A. This set has two subsets, the set itself and the empty subset. Now, let's look at another set, Y, with two elements, A and B. This set has four subsets, A, B, A and B, or the set itself, and the empty set. And finally, let's look at a set Z with three elements, A, B, and C. Now let's look at the subsets for Z. These subsets would be A, B, C, AB, BC, C, ABC, or the set itself, and the empty set. So now let us count and tabulate the results of what we just did. First, let's look at X. X had one element, and it had two subsets, or 2 to the power 1 subsets. Now let's look at Y. Y had two elements and 4 subsets, or 2 to the power 2 subsets. Now finally, let's look at Z. Z had 3 elements and 8 subsets, or 2 to the power 3 subsets. And so now we can see a pattern that the number of subsets in a set, n elements, is equal to 2 to the power n subsets. So now we are looking at the complement of a set. Sometimes we may be interested in the members that remain in the set when we remove a subset. For example, we can separate the letters of the alphabet, let's say set E, into two subsets, the set of vowels, say V, and the set of consonants, say C. If we remove the set of vowels V, then the set of consonants remain, and we can say that the complement of the set of vowels V is the set of consonants, C. This is written in symbols as shown. And so, in other words, the complement of a set is the set of all the elements that belong to the universal set except for those in the set itself. If the set is denoted by a letter, say A, the complement is denoted like this or this. We may also speak of the complement of a set in relation to another set that is not necessarily the universal set. The relative complement of sets A and B, denoted like this, is the set of all elements in A that are not in B. So let's look at some examples of complement sets. If the universal set is 2, 4, 6, 8, and 10, and A is 2 and 6, then the complement set of A would be all that remain in the universal set, which is 4, 8, and 10. Another example, say P is the set of A, B, C, D, E, F, G, and H, and Q is only the set of A, B, and C, then the complement of Q would be D, E, F, G, H when relative to P. Now let's look at equivalent sets. Two sets are equivalent if they have the same number of elements, though these elements may be different. And so, if set A and set B are equivalent, then n of A is equal to n of B. For example, let's say the set X is 4, 2, 7, 3, and 1, and the set Y is A, B, C, D, and E. As you can see, both these sets have 5 elements, and so X and Y are equivalent. And now let's look at another example. Let's say the set P contains the elements Mars, Saturn, and Jupiter, while the set Q contains the elements Jupiter, Earth, and Neptune. So, these sets are equivalent even though not all their elements are the same. And now let's look at equal sets. For two sets to be equal, they must have the same number of elements and also the same elements. That is, two sets A and B are equal only if all elements in A are also in B, and all elements in B are also in A. And let's look at some examples. Let's say X is a set containing the elements 4, 5, and 6, and Y is a set containing the elements 6, 4, and 5. X is equal to Y, and this is so because they have both the same number of elements and the same elements. And let's look at another example. Say the set P contains A, M, N, and T, and the set Q contains M, T, A, and N. These sets are equal, once again because they have the same number of elements, that being 4, and they have the same elements, albeit in a different order. So now let's look at an important part of set theory, Venn diagrams. Diagrams used to represent sets are called Venn diagrams. In drawing Venn diagrams, any enclosed shape is used to represent a set. The universal set, however, is usually represented by a rectangle, and other sets usually represented by circles or ovals. Venn diagrams show the relationships among sets, and one has to observe the relationships between them before drawing these Venn diagrams. So let's say U, or the universal set, is 2, 4, 6, 8, and 10, and A is 2 and 6. We can represent this information by drawing a rectangle for U and a circle or oval for A. The shape representing A has to be drawn inside of U because all members of A belong to U. Next, in the Venn diagram, we insert all the elements to complete the diagram, ensuring that no element is listed twice. But now let's look at drawing Venn diagrams for more infinite sets. Say U is the set of cars, S the set of sports cars, and R the set of red sports cars. Then R is a subset of S. The Venn diagram must show this relationship between R and S. And so the Venn diagram must show two sets, R and S, in the universal set. However, within S, R is drawn. Now before we continue looking at Venn diagrams, it is necessary to become familiar with two basic operations on sets. The first of which is the union between sets. So we may combine two sets to form another set, called the union of the sets. Let us assume that in a class, there is a set of students who study Spanish, let's call this set S, and a set of students who study geography, let's say set G. In this class, we shall probably find some students who study Spanish only, others who study geography only, and there may even be some who study both, and so Spanish and geography. This combined group of students is called the union of the sets S and G. For example, if S is A, B, C, D, E, F, G, and H, and G is G, H, I, J, K, and L, then the union between S and G, symbolized like this, would be A, B, C, D, E, F, G, H, I, J, K, L. To list the members of the union of two sets, let's say S and G, symbolized like this as we have seen, we will include all members of the set S and all members of the set G, making sure we do not list any member twice. And so, in other words, the union of two sets, say P and Q, is the set of all elements when both sets are joined or combined. And so the union of P and Q is denoted like this, as we have seen. And if an element, let's say X, exists in the union, then it must exist in either P or Q, or both. And now let us look at the other basic operation in set theory, the intersection of sets. As illustrated before, sometimes when we combine two sets, we notice that there are elements that are common to both. As we have seen in the Spanish and geography class before, sometimes children do both Spanish and geography. And so, the set which contains all elements that are common to both sets is called the intersection of the sets. In other words, if A and B are two sets, then the set of elements that are common to both sets is called the intersection and is denoted like this. And so, if an element X exists in the intersection of two sets, then X must exist in both sets. And so when intersecting sets are represented on a Venn diagram, the regions must overlap to show the common elements. This is shown on a Venn diagram like this, where the circles representing the set X with elements A, B, C, D, and E, and the circle representing the set Y with elements D, E, F, and G, overlap with the elements D and E in the overlap to show the intersection. And now let's look at what are disjoint sets. If A and B are two sets and they have no elements in common, then they are called disjoint sets, and so their intersection is empty, shown like this in symbols. For example, the set of odd numbers and the set of even numbers are two disjoint sets, or the set of vowels and the set of consonants, or the set of prime numbers and the set of multiples of 10. These are all examples of disjoint sets, joint sets. When disjoint sets are represented on a Venn diagram, they must be drawn separately. The sets must not overlap, as shown to illustrate that A intersect B is empty.